Hello, this video covers some introductory material on the periodic table. So the first thing I want to talk about here is a guy named Dmitri Mendeleev. Alright, he's a Russian chemist, as you see here, and what he did was he looked at the different elements known at the time and he tried to organize them into a system that made sense. And so he ordered them by atomic masses, but then he realized, well actually, I don't think he realized. It was someone later on realized that the atomic masses is not quite the right way to order it. You'll find some exceptions on your periodic table. But he ordered them according to atomic masses and then based on chemical and physical properties. And he got a pretty good organized periodic table created. And so he made a periodic table that looks similar in a lot of ways to what we have today. And he actually left some blank spots in this chart so that he knew that there were some elements that we hadn't discovered yet, and he said that we would find them eventually, and we did, so he did a really good job at this and created these blank spaces in his periodic table. And so this was really the guy that created the very basic periodic table. He did not include the noble gases because they're so hard to detect that people didn't know that they existed at that time, so he didn't include those in his periodic table, but they found them later and then they were added to the periodic table. This is what his periodic table actually looks like. Alright, or this is another version of it, and as I said, it looks kind of similar to ours. There are some similarities and some differences, and this is just using the elements that they knew at the time, which of course is not anywhere near the number of elements that we know right now. Okay, so when we found out that there was argon, this noble gas, and we looked at how it related to potassium, we saw that the mass idea was wrong, and so we organized it according to atomic number, which has to do with the number of protons, and so that's how it currently is. And this guy, Moseley, actually went through this process of rearrangement and developed a more modern periodic table. So Dmitri Mendeleev is kind of the one who came up with the original idea, but Moseley is the guy who kind of refined it into what we have today. And so again, with the current periodic table, there's something that we call periodic law, which is this repeating pattern that exists on the periodic table. In fact, the word period in this case means something along the lines of repeating. We see different repetitions of different patterns in the way that elements behave in each period of the periodic table, in each row of the periodic table. So I'm going to explain now a little bit about the way that we organize it and the different parts of it, and there are a lot of these things that you're responsible for knowing, so make sure that you kind of get to know these different groups and things like that. And so the first thing then that we need to talk about is that when we say the word groups or families, what we're talking about, typically speaking here, is the columns of the periodic table, and so they go up and down, groups or families. All right, and just like families that you think of it like families of people, the reason that they're called families is because they're similar to each other. So we have like this noble gas family that's drawn out here. They all behave sort of similarly. The halogens is another family. They have similar properties. The alkali metals have similar properties, and so we call them families when you go up and down in terms of the rows. And in terms of the columns there. Okay, now talking about the rows, the horizontal parts, those are called periods. All right, it's called a period, as I said, because the periodic table repeats itself every so often, right? And really, the patterns repeat themselves kind of every row. So every time you get to a new row, you're kind of restarting over all the patterns that you see in the periodic table. And we'll talk about some of those patterns here in a different PowerPoint, but that's why they're called that. This big black line here, what that does is it, generally speaking, separates the metals and the non-metals, although there are a few cases here where there are some elements that we call metalloids, which are sort of in the middle. But you need to know what things are metals and what things are non-metals. And so, generally speaking, that's one of the more fundamental classifications that we have in chemistry, so make sure you know where those lines are. One exception to this is that hydrogen, which is atomic number 1, that's a non-metal. All right, so make sure that you know that hydrogen is a non-metal. But other than that, the things that are on the right side of this bold line are non-metals, and the things that are on the left side of the bold line are metals. These ones also included sort of in the metalloids, although like Again, the metalloids is a weird class of elements, and depending on the periodic table that you look at, there will be different elements included in the metalloids, and sometimes, sometimes they don't agree. Something else, if you look up at the top of the periodic table, sometimes they're just numbered 1 through 18. Sometimes they're numbered with A's and B's. Sometimes we've got 1A and 2A, and then the column here that's labeled as 13A, sometimes that's called 3A. The whole business of the A and the B here is actually something that we call the main group elements, which includes these S and P block elements. So these ones are the main group. They're the ones that we talk about the most often. They're the ones where the patterns are most consistent. And so when we talk about the main group elements, the A group elements, these are the main ones. So know where the main group is on the periodic table. It's likely that something like that might come up on your exam. Oops, skipping that one. So now breaking down here some other parts of this, we're going to start talking about some specific groups. And so the alkali metals, that's this first column here, not including hydrogen. Make sure that you know that it's not including hydrogen. They're reactive, very highly reactive with air and water. And so if you drop an alkali metal in water, usually it will bubble and fizz and sometimes explode with fire, and it will react so fast that the alkali metal doesn't really even settle down into the water. It will just fizzle on the top and things like that. So alkali metals, very reactive. They're also really, really soft. Think about them like clay or like butter. And so you can take a butter knife and cut right into an alkali metal, and you see it looks just like a normal metal. It's shiny. It will then, very quickly tarnish over, but it's shiny and then, very soft. And then there are lots of alkali metals in compounds, but they don't exist as their own elements because they're so reactive. When we look at them, they're shiny, solid, and malleable. Malleable means that you can shape them into different things. In this case, you can shape them with your hands. So they're, as I said, they have a consistency that's sort of like clay, maybe like a really hard clay. The other thing here, they are ductile. Ductile means that you can pull on them and they will draw out into wires. And so I think about something like gum or like taffy. If you pull on it, it gets really, really thin in the middle and makes little thin wire-like things. And so this is what happens with the alkali metals. If you pull on them, they kind of come together in the center into like long, thin wires. The other thing is they're really low density and they have lower melting points relative to a lot of the metals, and so something to think about there. All right, so talking about the alkaline earth metals, those are group 2 or column number 2. They have higher densities and higher melting points than those alkaline metals, but they're not as reactive. And also, similar to the alkali metals, we don't find them much in nature because they're so reactive. Usually they're found in compounds in nature. And again, those are called the alkaline earth metals. Halogens, this is jumping all the way over across the periodic table almost completely to the other side in a group that we call 17A or 7A. The properties that these have, they're very reactive, all right? So you don't find halogens as single elements very often, as single atoms. Also, when we say they're toxic, I mean you don't want to ingest them in high quantities, and they're nonmetals. They react with metals like the alkali metals and the alkaline earth metals to make salts. All right, like sodium chloride is a salt and potassium chloride is another salt, and actually there's a bunch of them. Calcium bromide is a salt, lots of different things. And the other thing is we find them as these diatomic elements. So when you find them in nature, you don't find them as single atoms, but you find them as multiple atoms bound together, and so they travel kind of in little pairs. So when you find fluorine, it's like 2 little fluorine atoms bound together, and you find chlorine, it's 2 little chlorine atoms bound together, and so you don't tend to find them as single atoms. You find them in pairs like this. Next we have the noble gases. That's the last column on the periodic table. These are specially known for being very, very non-reactive with other things. All right, and then they're also colorless and odorless, and so I had mentioned this before, but it took us a really long time to discover the noble gases because they're so unreactive with things, and because you can't see them and it's hard to detect them in any way. The only way that we can really detect them is we know that they have mass, and so if you ever have a gas and you see that it has extra mass, you can kind of sense that maybe there's a noble gas there because it's taking up that extra mass in terms of things that aren't reacting. Hydrogen here is sitting above the alkali metals, but it is not an alkali metal itself. In fact, it's a nonmetal. It's a gas. It's also colorless and odorless, and is diatomic like the halogens are, so it's called H2. All right, and it's actually really, really uncommon in our atmosphere because it's so light that it reaches the edge of the atmosphere, which is called the exosphere, and then lots of it leaves off into space. And so something there. Hydrogen itself is in a lot of different things, and so it's one of the elements that's very essential to life. Carbon, nitrogen, oxygen, and hydrogen are like the really big elements in things that are alive. And so, yeah, very important for that reason. Next, this big chunk of elements here, which what we would call the D block, all right, those are called transition metals. When you think of normal metals like copper and iron and gold and silver and things like that, those are all transition metals. And so normal sorts of metals, and you don't really think of the alkali metals or the alkaline earth metals as metals because they don't exist in everyday life, but these ones, these transition metals, are the common ones. We see them all the time. All right. They're useful to us because they're not very reactive, and so things like if we want to make pipes or if we want to make jewelry or something like that, we're going to make it out of these because they don't react very much. They also have high density and melting points, which make them really strong and stable. All right, and then lots of these we have in our bodies, and so it gives us, here's an example. Iron is in hemoglobin, which is in blood. It's the part of blood that will store oxygen. And then we use them also, yeah, in a lot of building sorts of things. So the transition metals are pretty important to us for all of these reasons. The last one is called these rare earth, or these inner transition metals. They're called also the lanthanide and the actinide series. It's these ones here on the bottom. The lanthanides are less reactive than the alkaline earth metals, which, remember, are less reactive than the alkali metals. However, these are more reactive than the transition metals, so it's kind of hard. You got to keep all of that straight. They look just like normal metals. They're silvery, and they're soft, kind of like you would encounter with a alkali metal. When I say they tarnish with air, what I mean with that is, like, if you were to say cut into a lanthanide and then leave it exposed to the air, it would quickly film over with a tarnish, and so it doesn't stay shiny that long when it's exposed to air. And then it also reacts with water, but not to the extreme amount that like the alkali metals do. Generally speaking, a lot of times we'll use these as alloys, which, remember, alloys are mixtures of metals, and so we'll mix these things in. If we want some metals with specific properties, we'll put, a lanthanide in to try and give it its specific properties. The actinides, which are the very bottom thing on the periodic table here, those are really, really highly radioactive. It's because they have unstable nuclei. Thorium and uranium, these are natural elements, but many of the other ones in this series are actually artificial, which means that we only make them in a laboratory. And so some things there to remember about the actinides series. Sometimes we call these other elements here, they're kind of in the P block, but they're not part of a special group, and so we kind of call these the others. Sometimes if it's in that group 3A with boron, sometimes we call that the boron group, and the carbon group, and the nitrogen group, and the oxygen group. But because some of them are metals and some of them are nonmetals, they have sort of a smattering of different properties, and it's hard to group them into formal families like the other things that we have categorized. All right, that is it. So I went through a lot pretty quickly there. Generally speaking, the way that you have to study for this is you just have to look over the properties and try and learn what the properties are of some of these different elements, different families and things like that. And so it's a memorization thing. So just make sure you take some time to study this stuff and learn it as quickly as possible.